Hi everyone, welcome back to another video. So we're going through the practical electronics book, and in the last video I struggled a fair bit with some capacitor questions, so I'm hoping to do a little bit better this time out. Okay, so we ended up on determining capacitance, so let's do that as a little header. Determining. This is the good thing about taking notes, it actually forces me to learn to spell capacitance. Whenever I type, I don't spell, I just autocorrect. So the capacitance of a capacitor is determined by plate area. So you got plate area. So I assume plate area refers to the area of the two plates of the capacitor when it comes to getting positive charged and negative charged. I assume it means both plates, right? Plate separation. Plate separation defined as D. So I'm gonna assume this D refers to this gap here. Should probably move it a bit that way. Okay. An insulating material or dielectric. They didn't give the insulating material a name. Okay. So it could be air, could be ceramic. So let's do this. And we'll call that the insulating material. There's no symbol for it, but just so I know it's the color. Okay. So if a voltage is applied between the two parallel plates, voltage is applied between the two parallel plates, an electric field equal to, so if voltage is applied an electric field is produced. So electric field E. All right, and the calculation for that is E is equal to the voltage divided by the distance between two plates. All right, so from Gauss's law, I said that I'd check what this is. I didn't get around to it, so let's have a look at what Gauss's law is. Law. In physics, Gauss's law, also known as Gauss's flux theorem, is a law relating to the distribution of electric charge to the resulting electric field. Okay. Um. Uh. Yeah, I'm looking at all of these, and I'm just like, none of this is in English. Like, it's all just these physics symbols. Hmm. Okay. Fine. Guess I don't need to know them. So each plate must contain an equal and opposite charge. Okay. I'm going to try and learn the definition of this law at another time. So each plate must contain an equal and opposite charge. Each plate must contain an equal and opposite. Yes, of course. Yeah, that's true. So Q charge is equal to the permittivity of the permittivity. Oh, it's just permittivity of the dielectric. Okay, of the insulator times by the area of the plates multiplied by the electric field produced. and this equals the charge on each plate. Okay. So charge on each plate, right? So this, probably better to draw it the other way, but okay, it doesn't matter. So the charge on each plate, right? To calculate that, you get Q is equal. Is this Q for both, or yeah? Because they're gonna have equal opposite charges. So it'll be equal and opposite. Okay. So I'm gonna assume this charge is for them each, right? So we've got this little weird free thing, which is the permittivity. Okay. And then we've got multiplied by A. I like to put the multiplication symbol. I know that people don't, but it helps me out. Multiplied by E. Okay, so let me just break up this because I know they've now just replaced the E with voltage divided by the distance, because obviously we've just set up here that it is that. But let me just stages. Let me go in steps. So this one here is the permittivity. This is the permittivity of the dielectric, right? So for example, air or ceramic. Okay, so let's see, like, what's the permittivity of just room temperature air? By definition, a perfect vacuum has a relative permittivity of exactly 1. Okay? Air has a relative permittivity of K air is equal to 1.00006. So it's similar, it's close to a vacuum, but not a vacuum. Permittivity of free space is a physical constant used in electromagnetism. Relative permittivity. Relative permittivity or dielectric constant of a material is its absolute permittivity expressed as a ratio relative. I want the definition. In electromagnetism, the absolute permittivity, often simply called permittivity and denoted by the Greek letter epsilon. So this is called epsilon. Epsilon. I'm super comfortable with Ohm's law, like the Ohm symbol. Like when I see that, I know it means ohms, and I hope that I can start to get comfortable with the other symbols, because I'm really not right now. Really not comfortable with them. When I see them, like I get anxious. Okay, so epsilon, so is a measure of the electric polarized. How do you say that word? Polarizability. Polarizability. You got polarize and ability. Polarizability is a measure of the electric polarizability. Let's just see how to pronounce that, because I'm gonna say it on YouTube 50 times. May as well pronounce it correctly. Fine. What? Isn't Google supposed to define it? Hmm? Define. What? I'm sure YouTube's supposed to define stuff when you put define. Anyways, okay. Pronounce. How to say polarizability. Oh, you're not gonna be able to hear it. One sec.
Polarizability. Polarizability.
Polarizability. Polarizability. There. Polarizability. 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 Cool. Okay. So, all right. I bear in mind, I haven't studied physics at all, so like nothing. I mean, except for when I was like 16, I didn't pay attention anyways. So I kind of need to go back through all of this stuff as well. So the permittivity of the dielectric, and so this actually means polarizability is a measure of how easy an electron cloud is distorted by an electric field. How so polarizability. This is how easy tendency of a matter subject to an electric field to acquire an electric dipole. First, the tendency of matter when subject to electric field to acquire an electric pole dipole moment. I don't know. Polarizability is a measure of how easy an electron cloud is distorted by an electric field. How easy, um, how easy electron cloud is distorted. Doesn't really make sense to me. Electron cloud polarizability molecule is a measure of its ability to respond to an electric. Okay. How easy a material, can I just say it gets polarized? Responds to an electric field. Yeah, I'm kind of it's not the best, but okay. All right, and then so A is the area. Now I would like to find out from here, is this the area of both plates or the area of just one plate? Not super clear, is it? Oops. Where E is the permittivity of the dielectric free space vacuum. Okay, yeah, this is that free space stuff. Okay, anyways, so I wanted to know here, determining capacitance. Area of plates. The generalized equation for the capacitance. Okay. And the larger the area of the plates, so this refers to them plurally. The ability of a capacitor to store a charge on its conductive plates gives it its capacitance value. Capacitance can also be determined from the dimensions or area A of the plates and the property of the dielectric material of the plates. Yeah, so it seems to me that it's plural referring to both plates, right? Hopefully that's what you get away from it as well. Be good if even if we're wrong, then at least we're both wrong. Yeah, I don't like it. All right, so we got area of plates, and then E is the electric field, right? If a voltage is applied between the two parallel plates, an electric field is produced. Okay, so E is the electric field. So what I'll do is I'll actually test myself. I'll make questions and I'll test myself on what these are. The area of plates, and E is the electric field produced by the voltage. Okay, cool. So now what we can do is we can replace E with V over, that's put V over R. Wait, V over D. Too much Ohm's law. we can replace E with V over D because E is equal to V over. Cool. Okay. So then that leaves us with Q is equal to what was this thing called again? Epsilon. Is that like a printer? Isn't that a printer company? Epsilon or Epson? I'm thinking of Epson. Epsilon times area times voltage divided by the distance between the two plates. Oh, they've done it like this. Oh yeah, because of what's it, order of operations? What's it called? BODMAS thingamajig? Yeah, okay. So it works at that. That's the same thing, right? But anyways, I'll write it like that anyways. Do it the same. 3 AB divided by D. Cool. You see, look at this, yeah. I don't how long I don't know how long this video's been going for. I'm gonna say 15 minutes just for me to do this. It's slow, man. It's slow, but yeah, this is me. I'm not. Because I know that I haven't been in education. You know, from the ages of what, uh, 18 to 28, and then to add to that, when I was in education, I didn't pay much attention, anyways. So I don't expect that I'm gonna be able to pick things up fast. So I just know that I'll get top grades because I just put in the work, as opposed to just, relying on the fact that I'm gonna be able to pick it up fast. All right, so this is about the free space vacuum. So I'm just skipping over this because I can't imagine that I need to know. Like, firstly, I don't even know what those things are. Like, what's N? What's M squared? Is that the area, the meter per meter squared, and N is newtons, and D is coulombs. I don't know. Who knows? I'm not bothered anyways. So the constant EA over D. So you've removed voltage. Why have you removed voltage? Okay. The constant EA over D term in the equations is the capacitance. Did we learn that before? I don't know. Didn't we learn capacitance is something else? Um, Capacitance was charge divided by voltage. Oh, okay, yeah, because we're saying that um, capacitance of a capacitor is determined by the plate area separation. Wait, no, I'm confused. Okay, let's go up. What did we learn capacitance as? We learn it as charge divided by voltage. Okay, so let's draw a line under that. And let's just write this bit out again. E is equal to Q divided by V. Okay. And then what we say in here, we're saying here now that C is equal to, what's it called? Not epsilon. That's a good way of me remembering what it's called though. It's not epsilon, it's epsilon. Epsilon, right? So you got a little epsilon guy, epsilon. A, the area, divided by D, the distance between them. And so we're saying that these equations are the same. Why is that? I don't get that. So V over D is V over D is the electric field. Capacitance, you're saying we've said previously that it's charge divided by voltage, and now we're saying that it's epsilon times area divided by the distance between the two plates. You're not even gonna explain it, huh? So okay, let's think about this. Think about it. What we're saying is that this part of the equation here, this part, this part, this part here is all. This is capacitance, but capacitance is also charge divided by voltage. So how would you work out charge normally? Man, I'm confused. I don't get that. I'm gonna have to move on because I don't want you to get bored and be like, idiot, Hamid. This, obviously, it's just this. I don't get that at all. The constant EAD term. Okay, that's fine. Don't worry about it. The relative permittivity of a material. So permittivity is its ability to get polarized, right? The relative permittivity of a material what? Okay. Oh, reference. Sorry, reference referred to. Reference to the permittivity in in vacuum. Okay. So you're comparing inside a vacuum the ability for electrons to get polarized versus the material itself. Okay. So you reference those two things together, just like for example, if you was referencing a point in whatever circuit to ground, referencing it right. Okay. That's what that means. Is referred to as the dielectric constant. Okay. Yeah, I'm alright with that. So you just okay, because we're just comparing it to it's basically like voltage, but for permittivity. You're just comparing it to instead of comparing it to zero or ground, you're comparing it to a vacuum, right? Which I assume the vacuum is the hardest place for electrons to get polarized, or would it be the easiest? I don't know. I don't know. In space or in a vacuum, nothing in there. You wanted to polarize electrons. Yeah, I don't know if it's easier or harder, but anyways, that's fine. We reference it to it. Okay, I'm okay with that. So let's just write this down because I'm gonna need to learn that, I suppose. I don't think I'm not gonna bother learning the equation for the permittivity of a vacuum. I mean, I could just Google that. Like, give me a break. Um. Okay. So let's talk dielectric dielectric constant. Okay. So um, wondering how to arrange my notes here. Thinking. Okay. So let's do this, right? I don't want my notes to be scary. That's the thing. Because if I, for example, let's say I do another 20 videos of this series, right? Then I come back to look at this particular video and I've forgotten all of it. And if I see this equation here, this vacuum one, I know I'm just going to be like, nah, we'll revise that tomorrow. I'll just go do some C programming or something. So I need to try and, with these subjects that I'm struggling with, because if this was a C programming book now, I'd be flying. I'd be loving it. But this side of things, I really, really suck at. And so I really want to try and basically baby myself and look after myself, you know. You know, one of those things where it's like, you know, if you need to read a book and you was just terrible at it and you hated it, you put like Starburst or whatever every 5 pages so you can have a Starburst every 5 pages. That's the kind of stuff that I need to do for myself. So anyways, this what's this thing called? Epsilon thing? This epsilon zero is um it's the permittivity. The permittivity. No way I can spell that word. You guys know what that means, right? What that says. The permittivity. Did I spell it right? I spelled it right as well. The permittivity of a vacuum. Of a vacuum. Right, and then I can just I don't want to write the equation. 8 uh 8 times 10 to the minus 12 these over 12 over n 2. No. Okay, I'm gonna leave it. I can always I can just Google that, right? The permittivity of a vacuum. Okay. So relative permittivity of material, reference to the permittivity in a vacuum is reference to dielectric. Okay, so we reference permittivity. I'm going to be saying this word in my sleep. We reference permittivity to the. I can just put E0 now because, or whatever it's in epsilon. The epsilon 0. Wait, let me just add a bit more words there. I don't think I'm going to understand that in the future. We reference permittivity of materials to, yeah, E0. Okay, and so this looks like, okay, wait. This is, K. Yeah, let's go with that. So then K is equal to epsilon over epsilon 0. If I saw that, I'd think that was Arabic. That's crazy. To be honest, it probably, oh, it's Greek layer, isn't it? And this is called the dielectric constant. What is that equation? Okay. Oh, nice. Okay. So plugging this into the previous equation, the previous expression, we get the capacitance in terms of dielectric constant. So why did you plug that in? I don't get it. Oh, okay. Oh, okay. Because basically, so this thing here doesn't have a value because that's not how we refer to it, right? We don't refer to epsilon as epsilon. We refer to it as relative permittivity to an object. And the relative permittivity of an object is K epsilon 0. Wait, why is it K? Shouldn't you just put K there? Why are you putting So this bit here is permittivity of a vacuum. This bit here is how the permittivity of a material compares to a vacuum. And that's the area. I don't know. Why is this twice? Like, shouldn't we only need this once? Okay. I just need to keep telling myself it doesn't matter. Just memorize the bloody equation. Learn the equation and live with it. This is what I need to do more. Because you don't have the time to learn all of this stuff, you know. Save this stuff for if you want to go and get a master's and PhD. All right, so let's just plugging this into um into C equal to epsilon A over D. Then you get C. So this is capacitance is equal to K epsilon 0 A over D. Man, I'm not happy with that at all. Like, that's just an, yeah, anyways, it is what it is. What can you do, man? Electricity is not simple. Okay. How much more do we have to go here? My brain's like already fried now. Commercial capacitors. All right. So it's all right with you guys. We'll finish. We'll get up to here. That might take me another hour. Okay. All right. Let's whiz through it. Come on. So C is in farads, A is in meters squared, and D is in meters. Okay. I didn't even consider that actually. So D is in farads. Farads like Harrods. And A is in meters squared. Meters squared. And D is in meters. Why would D be in meters when you're talking about the distance between two capacitor plates? I mean, are there capacitors in the world that have a meter of difference between them? The big bloody capacitor. Bit strange now. You need to stop asking all these questions to bloody study. The dielectric constant varies from 1.00059 for air, one at one at the moment. What's ATM in school speak? I just think of it at the moment, tech speak. One at the moment. What time is it? One at the moment. Okay. To over 10 to the 5, 100,000 for some types of ceramic. Okay, so don't know if I need to know that information. Okay. Well, maybe the ceramics. Okay, so because I don't want to be surprised by some value. So, uh, K, meaning the dielectric constant, can be 1 to 100,000. Okay. Table 2.6 shows the relative dielectric constants for various materials often used in construction capacitors. 2.6, which is here. So you got a vacuum, which is 1, air, 1 at the moment, ABS, plastic, for 3.8. So, okay, so look, so water is 80, and that's got a lower score than 1, like infinite, and air 30 to 70. What 2.4 to 3.8 has 410. I don't get the strength thing. Dielectric constant, dielectric strength. How do these two relate? What is dielectric strength? What's meant by that? What's meant by dielectric strength? I said that I was through it and now I'm googling more stuff. Dielectric strength. In physics, the term dielectric strength has the following meanings. For pure electrically insulated material, the maximum electric field that maximum electric field that the material can withstand. Maximum electric field. Okay, so dielectric constant. What's the dielectric constant again? Dielectric constant is the the permittivity, so the ability to polarize it. Okay, I'm gonna have to skip over this bit. I don't particularly understand it. Where are we? Okay, so capacitors often have more than two plates. Oh yeah, that's true. Yeah. Well, only just one plate, two plates rolled up. The alternate plates being connected to form two sets as shown in the lower drawing. Two sets. Okay, sure. Oh, I get it. Yeah. Basically, plate, insulating material, plate, insulating material, plate, insulating material. Got it. This makes it possible to obtain a fairly large capacitance in a small space. For a multiple plate capacitor, we use the following expression to find the capacitance. N minus 1. Okay, so that's an important point. So for multiple plate capacitors, bear in mind this book here is practical electronics for inventors. So this is like fairly dumbed down, low level stuff. So if you're watching this like me and you're like, this is difficult, we're dumbos, okay? We need to step up our game. This Some of the other books that I've seen are an absolute joke when it comes to teaching this stuff. This would be like the first sentence of each chapter. Anyway, so What happened to whizzing through it? I talk too much. Dielectric. What's K again? Dielectric constant. And then that's times by the epsilon 0. And then that's times by the area. All of that divided by the distance between them. And then that's times by the number of sheets minus 1. Got it. Where the area is in meters squared, the separation D is in meters, and the number of plates N is in integer. So N is equal to number. That's fairly obvious, but I'll try that anyways. Number of plates. Example. I can't do an example, people. Oh dear, this is painful. Let's do it. Go on. I think I deserve a pizza after this. What is the capacitance of a multiple plate capacitor containing 2 plates? What is the capacitance of a multiple plate capacitor containing 2 plates? What? How is it a multiple plate capacitor with 2 plates? Isn't it just a capacitor? Anyways, each with an area of 4 centimeters squared, a separation of 0.15 millimeters. That's what I'm saying. I was like, why do we test it in meters when, the separation for a capacitor is going to be 0.15 millimeters, not even 1 millimeter, tenth of a millimeter, and a paper dielectric. They've got you. You have to use the table. That's brilliant. That is brilliant. That is good, because that's very realistic. You're gonna go and use paper. Where's paper here? Am I blind? I can't see paper. Where's paper? Vacuum air, ABS glass, the neoprene, plexiglass. Paper have another name? Oh, paper, bond, paper. There we go. Interesting. Okay, this is gonna be fun. All right, so I'm glad I decided to do it. I was I was looking to skip it, to be honest with you. I mean, I believe it. If you watch my other videos, you know I skip this stuff. Okay, so we've got an area of 4 centimeters squared, and that's times 2 because we've got 2 plates. And then we've got D that is equal to 0.15 millimeters. So am I gonna have to convert that to meters? I think I am gonna have to convert it to meters, right? I'm gonna use Google. I can't. Sorry, I know this is embarrassing. It's D. So D is equal to 0.00015. So basically, you just went up 1,000 times 10 to the 3, so you just added 3 zeros. Okay, that's fine. So D is equal to, and then we've got paper statistics, and paper it was 3.0, wasn't it? In terms of the dielectric constant. Check. Paper 3.0. Do we need to know dielectric strength? No, we don't. Okay. So, what do we need to do now? We need to take this equation up here because apparently it's a multiple capacitor. Multiple sheet capacitor. I don't get what that means. That is what it is. So we've got C is equal to K epsilon 0 A over. Oh, am I going to have to do the epsilon 0 equation? I don't even know what that stuff means. I can't do this. Not possible. I don't know how to do these things. Wait, did they tell us? Did they tell us the value of the epsilon? That's 1.00059, right? Vacuum 1. So can I just assume that all of this page is just 1? I'm going to do that. I'm just going to assume it's 1 because I'm putting 8.85 times 10 to the minus 12 c squared over n times m into. Get that, man. I'd rather skip it. Okay, so what I'm gonna do, I'm gonna have to do this. I'm gonna do C is equal to K, which is 3, right? Said K is 3, right? Relative dielectric constant 3. Okay, K is 3, so this is K here. Then we've got. Oh, I'm stressed out with this. And I just put. Let me try and get. Um, epsilon naught value. This is painful, man. This is painful. Can I put 1 or not? I really don't. I'm stuck here. To be honest. Standard value. This is frustrating, man. I was excited for this thing, but I'm not now. I just don't want to put it all in. Okay, so I'm just gonna do times 1 because yeah. All right, times the area, which is 4 uh 4 centimeters squared. So is that times? Do I times that by 2? So we've got the capacitance of a multiple plate capacitor containing 2 plates, each with an area of 4 centimeters squared. So is that um each with an area of 4 centimeters squared? So yeah, I'm gonna have to do 8, right? Okay, I don't know what to do. I'm gonna go with 8. Okay, and then a separation. Okay, so all of that then divided by d, which is 0.00015. If I get close, I'll be happy. The reality is, well, what one thing I know is, which is true, that if I do this in an exam, as long as I start using the equation, even if I put in mumbo jumbo values, you still get marks for it anyways. Divided by 0.0 complex infinity, 0.20315. That's equal to 1,660,000. Uh, Mate, I was beyond wrong. Look at this. Oh, I forgot the n times by. But even still, I was beyond wrong. Yeah, I don't know. I don't know. I don't even know. I have no way. No, I don't know how I could put that into a calculator. So yeah, 70. Apparently, it's 70. Well, give it a go yourself, guys. I had a lecturer do that to us last year. It's funny. Just got it wrong, and then it was just like, "Oh yeah, well you guys give it a go." Okay, how much chance do we have? Anyways, hopefully you guys have a greater chance than I do. I don't understand that, and yeah. I mean, this is the first time I'm learning this stuff, so I'm not really too bothered if I don't understand it. So hopefully I'll be able to understand it in at some point. All right, guys, thanks for watching. I'm gonna go eat something. Yeah, hopefully. I don't know. That's I don't know. Yeah, if you can tell me how to put that into a calculator, I'd appreciate it. I mean, I'm probably not even waste time because I doubt I'm going to do it. But 1.5 times 10 to the... Okay, so that's the... They've only times it by 4 here as well. Look, so they have 8. Strange, because they said that each plate has an area of 4 centimeters squared. So why would we only do it by 4? I got the 3 bit right at least. Yeah, I forgot the m minus 1. Okay, that's fine. Anyways, next video we'll go into commercial capacitors. Thanks for watching, guys. See you in a bit. Peace.